Hi, I'm Zach Phillips, and I'm here to talk to you about my final project presentation for CS 294, Computational Photography at the University of California at Berkeley. My project was Fourier Filter Camera, which was an Android application that allows you to see the Fourier spectrum of your scene, and also perform some filtering interactively by drawing on the screen. So my motivation for this project was that frequency analysis is a really important concept to grasp for both image processing and also optical hardware design. Two-dimensional Fourier transforms are a very useful schematic for understanding the 4F system, or like an infinity-corrected microscope. And also, frequency analysis is very useful for image processing methods, as we learned in this class. On the optical hardware design, it influences depth of field, optical resolution, and also the choice of sensor size or sort of pixel pitch that you might pick for your sensor. However, 2D Fourier transforms can be a little bit difficult to understand. There's sort of this intuitive switch from temporal to spatial frequencies that might take a little bit of time to understand. And also, the extrapolation to two dimensions can be a little bit sort of conceptually hard to grasp at first, even though they're separable and it's basically doing the same thing in two dimensions as a 1D temporal Fourier transform. Um, also, Fourier transforms or Fourier spectrums are scene dependent. So if you take a single image and do all your analysis on that one image, you really can't get a intuitive grasp of the two-dimensional Fourier transform. So I wanted to build an application that allows students to look at a variety of scenes just by pulling their phone out of their pocket and sort of looking at it in real time. So they can sort of get a better grasp of, like, say, what an aperiodic or a periodic scene, such as maybe a fence or a laptop keyboard, might look like. So I wanted to provide a little bit of mathematical background for my application and the methods I'm about to describe. So on the left, we have the inverse Fourier transform, where we go from the Fourier domain to the real domain. Both of the equations on the top here are in the continuous case. On the right, we have the equation going from the real domain to the Fourier domain. This is known as the forward Fourier transform. The one on the left is known as the inverse Fourier transform. The images above this correspond to the resulting images of these transforms. The one on the left is the image that's first acquired from the camera. If we take the Fourier transform of this, we have the image on the right, which is a result of the equation below it. So these images are screenshots of my app. These images are streaming at 20 to 30 frames per second, depending on the resolution the user chooses. At the bottom, we have the discrete version of the forward Fourier transform. This is the equation that we actually use in this application because all of our images are discretized, where m and n are the height and width of our images, respectively. So at its most basic level, this application is a camera that computes the Fourier transform of the incoming camera frame. This allows the user to walk around a scene and just sort of see what the Fourier spectrum of different images might look like in real time. So these frames come at roughly 20 to 30 frames per second. You'll see the Fourier transform images at the bottom left of both of these screenshots. At the top, we have the inverse Fourier transform button, which lets the user go from the Fourier domain to the real domain. At the bottom, we have sort of the result of pressing that button, which is the actual camera frame. This allows the user to quickly toggle between the camera frame and the Fourier transform of that frame, to sort of give an intuitive grasp of what it means to take a Fourier transform of a different kind of scene. As I sort of developed this proposal, I thought that this might be a good chance to sort of demonstrate the effects of filtering in the Fourier domain on images. So I developed an interface that allows the user to draw a filter on the screen, which is then applied to the real space image, which would be at the bottom here. The users can also invert this filter to sort of have like a low pass and high pass type filter to sort of give some intuition as to what sort of filters mean, also for different kinds of scenes. I also provided an interface for box filters, circle filters, and annulus filters, or bandpass filters, so just to sort of allow the user to draw, like, some pretty standard filters without actually drawing them meticulously with their fingers. So I think the result is a really simple and intuitive interface for demonstrating the usefulness of the 2D Fourier transform and sort of conveying a better intuition than sort of like a programming assignment on a static image. So the imaging pipeline for this device was intended to work exactly like sort of your two-dimensional Fourier filtering system. In hardware, it mimics a 4F system, although all this processing is performed in software. So we receive a raw camera frame from our device's camera. This is recorded in real time. We only observe the real part of the spectrum. Camera pixels are not direction sensitive unless you go with a Litro camera, which has lens-lit arrays. They can also detect the incoming angle of light. In this case, we just have a standard cell phone camera, so we can't measure the phase. When we perform the Fourier transform, we get a complex image, which we can then perform, just get the magnitude squared of, and take the log of this to display on the screen. This has also been mapped to a color map to aid in the visibility of the spectrum. Once we have this, we multiply it by our binary array, which is drawn on the screen by the user. Here we have the smiley face that I've drawn with my finger. We then inverse Fourier transform this filtered array, and we have our final image. And this is displayed in real time on the screen as the user can move their camera around and check things out. They can also reset the filter at any time and invert the filter from this interface. So a little bit about drawing filters. We can draw filters by hand. So here we can do, say, just a very low frequency passband in terms of Y, but a wide range of frequencies in X, and we can observe what that looks like. The smiley face filter I mentioned before. We can also have predefined filters that are resized using the fingers, using the user's fingers. So you can just sort of set the size of the filter. And this works for both circles and squares. And we can also invert these filters from low pass to high pass using this button at the bottom right of the screen. So here's a few slides of results, just sort of to convey the intuition for the way this project works. So as you can see, if we block the DC term and all of the X frequencies, we see all of the sort of vertical edges in the scene, and not really any of the horizontal edges. Likewise, if we do the same thing in the other dimension, we see all the horizontal edges, but none of the vertical edges very well. This is also mimicked for this scene. This is just on my keyboard. So you can see that the keys have sort of different edges highlighted based on our corresponding filters. And you can see in both cases we block the DC, which is why this seems sort of like a silhouette or maybe a Sobel transformed image, like a derivative type thing. Likewise, an X filter will give us no frequencies sort of at the edges of our scene, but a cross filter will take away sort of all of the vertical and horizontal edges, which are a lot of the scene just because our world is mostly horizontal and vertical, particularly like buildings and things like that. So we really get much less information if we block these frequencies. So let's see. Likewise, in the top case, we have a lot of resolution in our X dimension, and not very much in our Y dimension. This image looks reasonably good just because we still have our DC passband, which is why it looks more like an actual image. But there's sort of some anisotropic effects of the filtering here. And again, our smiley face filter we showed before. So again, the inverse X, we sort of see the artifacts of the filter there as the convolution happens. And then if we just allow a line here, this line has sort of been tilted, so we get a lot of weird effects. But you can sort of see that the image is pretty blurred because we only allow a very narrow range of frequencies to pass through. So we have some high pass filters here. These generally highlight edges or high frequency effects. If we have a larger filter, we see generally less information because there's less information in our energy in our sample. In the bottom case, we have more energy and we sort of see more of the low frequency effects. So we have more information in the image. Again, some low pass filters. So if we have a very wide frequency coverage, we have a pretty high resolution image. And it turns out the resolution of your image, or the width of your point spread function, as we call it, is related to the Fourier coverage. So in the top case, we have a very broad coverage in the frequency domain. When we inverse Fourier transform this becomes a very small peak that's convolved with our image. So we have pretty much the same image we started with because that's on the order of a pixel or so. Conversely, if we have a very small coverage in Fourier space, that becomes a very broad point spread function. So effectively, this bottom image has been convolved with a sort of a wide sinc function or a double sinc function because this is a two-dimensional rect function. Interestingly, if we block half of the Fourier spectrum, we really don't see that much of a difference. This is because our scene doesn't have that much phase information, which is sort of encoded in asymmetries in the Fourier domain. We also here have included the DC, although it's not completely obvious. If we block the DC, there'd be a very different sort of picture. And if we take this away, we see almost the same image. We have half the power, obviously, because we have or double the power, sorry, because we have double the spectrum. But essentially the same information because we're not looking at anything to do with a phase image. This is because the camera takes the intensity of the incoming electric field. So we really know nothing about the phase of the light coming in. A few more examples. With the circular filters, again, a larger filter gives us better resolution than a smaller filter. Um, so these are annulus filters. These basically, in this case, is just a band stop filter. So we can really see in the top case that we have just sort of blocked this band of frequencies. And that really doesn't remove much from the image. I mean, the image is, you can see a few artifacts here and there, but there's really almost the same image in the top case. In the bottom case, because we blocked sort of lower frequencies, which are generally more have more effect on image quality, we start to see a lot of blurring. We can still sort of make out the image, but we have artifacts because we've just sort of gotten rid of these frequencies in the image. Likewise, if we make these band pass filters where we just have a very narrow range of frequencies, this is sort of like our frequency domain blending project we had for this class. You can sort of see the different information, different frequencies. As we go to really high frequencies, we only see the very, very sharp edges, which are really not that common in the image. That's why the bottom image is almost completely gray. So this is a video of the app in action, just to show that it actually works. So we can set the size of our filter using our fingers, and here you see a small filter gives us poor resolution. We can choose between a few different types of filters. Here's the circle filter. And again, you see a large filter gives us good resolution. We can also do half filters, and we can set the size of these. This is, again, demonstrating the phase property of these filters. So really not that much information is lost just by doing half of the Fourier spectrum. Here's the full spectrum of the image. And here is our annulus. So again, blocking frequencies doesn't do very much, but only passing a narrow band of frequencies really sort of degrades the quality of our image. And if we make this smaller, we actually get more information. This is actually a really cool image, I think. We can really see the highlights of the high frequency or sort of medium range frequencies. We can also touch the screen to save a picture, which is a nice feature for saving for later. I also have a settings menu for setting the resolution, so we can change the speed of our, or sort of the frame rate of our camera. So there's also a color mode. It's optional for speed purposes. Finally, we have a freeform drawing mode where we can sort of draw on the screen and have these filters be interactive. And I think this is where this device really shines. So here we've drawn a smiley face, which is just a bandpass filter, or sorry, bandstop filter. Now this is a bandpass filter, and we have really nothing. If we block our DC, we're going to have a lot stronger effect. So again, we have a similar filter to our annulus. And finally, I'd like to thank you for your time. This has been my final project presentation for CS294, and you can see the result of the CS294 filter right there. So thank you very much for your time. The source code for this application is on GitHub. Here's my website. And there's also an installable APK that you can sideload onto your Android device. Android 4.4 and above are currently supported. This device needs the open source OpenCV library, which it will prompt you to download. But I encourage you to check out my code and expand upon it, and let me know if you have any feature requests or bugs. And thank you for your time.